Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the technical report of Kimi K2 titled Kimi K2 Open Agentic Intelligence. Are you ready to explore one of the most advanced open-source large language models to date?
Absolutely. I've been looking forward to this. Kimi K2 is making waves in the AI community, especially with its focus on agentic intelligence. To start, can you explain what agentic intelligence means in the context of large language models?
Of course. Agentic intelligence refers to a model's ability to autonomously perceive, plan, reason, and act within complex and dynamic environments. Unlike traditional models that rely on static imitation learning, agentic models actively learn through interactions, adapt their behavior, and acquire new skills beyond their initial training data. This is a significant shift in the development of LLMs.
That's fascinating. So, Kimi K2 is designed to push the boundaries of agentic capability. What are the main contributions of this model, according to the paper?
The paper highlights several key contributions. First, Kimi K2 introduces muon clip, a novel optimizer that combines the token-efficient muon algorithm with a stability-enhancing mechanism called QK clip. This allows for stable pre-training on a massive scale, 15.5 trillion tokens, without any loss spikes. Second, the team developed a large-scale agentic data synthesis pipeline to generate tool use demonstrations in both simulated and real-world environments. Third, they designed a general reinforcement learning framework that combines verifiable rewards with a self-critique rubric reward mechanism, enabling the model to learn from both external tasks and its own outputs.
That's quite comprehensive. Let's break down the pre-training process first. What makes muon clip different from other optimizers like AtomW?
Great question. Muon clip builds on the muon optimizer, which is known for its token efficiency. However, when scaling up, muon can suffer from training instability due to exploding attention logits. QK clip addresses this by rescaling the query and key projection weights whenever the maximum attention logit exceeds a set threshold. This keeps the training stable and prevents loss spikes, which are common issues in large-scale LLM training.
Interesting. So QK clip acts as a safety mechanism during training. How does this impact the overall training process and model performance?
The results are impressive. With muon clip, Kimi K2 was able to pre-train on 15.5 trillion tokens without a single loss spike. The training loss curve remains smooth and stable throughout, which is a testament to the effectiveness of QK clip. Moreover, experiments showed that QK clip does not degrade model performance, maintaining the optimization characteristics of muon.
That's reassuring. Now, let's talk about the data. The paper mentions improving token utility with rephrasing. How does this work, and why is it important?
Token efficiency is crucial when high-quality data is limited. The team used synthetic data generation, specifically rephrasing, to increase the utility of each token. For knowledge data, they employed style and perspective-diverse prompting, chunk-wise auto-regressive generation, and fidelity verification to create diverse and high-quality rephrasings. For mathematics data, they rewrote documents into a learning note style and translated materials from other languages into English. This approach improved model accuracy and generalization without overfitting.
That's a smart way to maximize the value of available data. What about the model architecture? How does Kimi K2 compare to other models like DeepSeek v3?
Kimi K2 is a 1.04 trillion parameter mixture of experts MoThi transformer model with 32 billion activated parameters. It uses multi-head latent attention MLA and has 384 experts, compared to 256 in DeepSeek v3. The number of attention heads was reduced to 64 to optimize inference efficiency, especially for long context processing. The architecture is designed based on empirical scaling laws, balancing performance and computational cost.
The scaling law analysis is intriguing. Can you elaborate on the sparsity scaling law and its implications for model performance?
Certainly, the sparsity scaling law shows that increasing the total number of experts while keeping the number of activated experts constant consistently lowers both training and validation loss. This means that higher sparsity, more experts, fewer activated per token, improves performance without increasing computational cost. For Kimi K2, a sparsity of 48 was chosen, activating 8 out of 384 experts per forward pass.
That's a significant architectural decision. Let's shift to the training infrastructure. How did the team manage to train such a massive model efficiently?
The training was conducted on a cluster of NVIDIA H800 GPUs, with each node containing 2 TB RAM and 8 GPUs connected by NVLink and NVSwitch. The parallelism strategy combines 16-way pipeline parallelism, 16-way expert parallelism, and ZR01 data parallelism. This flexible approach allowed the model to be trained on any number of nodes that is a multiple of 32, optimizing both memory usage and computational efficiency.
Managing activations must have been challenging with such a large model. What techniques did they use to handle activation memory?
They employed selective recomputation for high-footprint stages, FP8 storage for insensitive activations, and offloaded remaining activations to CPU RAM. A copy engine streamed the offload and onload, overlapping with computation and communication kernels. This ensured that activation memory fit within GPU constraints, preventing crashes due to expert imbalance.
That's quite an engineering feat. Now, moving on to post-training, what does the multi-stage post-training process involve?
Post-training includes supervised fine-tuning and reinforcement learning. The supervised fine-tuning uses a large-scale instruction tuning dataset, generated through a combination of human annotation, prompt engineering, and verification. For agentic data, a synthesis pipeline creates tool use demonstrations, teaching the model to interact with tools in multi-step, interactive scenarios.
The agentic data synthesis pipeline sounds complex. How does it work, and what makes it effective?
The pipeline has 3 stages: tool spec generation, agent and task generation, and trajectory generation. They built a repository of over 3,000 real-world tools and 20,000 synthetic tools, covering a wide range of domains. Agents are generated with different tool combinations, and tasks are paired with explicit rubrics for evaluation. Trajectories are generated through simulated user interactions and tool execution environments, with quality evaluation and filtering to ensure high-quality data.
That's impressive. The hybrid approach with real execution environments adds authenticity, especially for coding tasks. How does reinforcement learning fit into the post-training process?
Reinforcement learning is used to further improve the model's capabilities. The team developed a gym-like extensible framework for RL, covering a wide range of tasks with verifiable rewards. For subjective tasks, they introduced a self-critic reward mechanism where the model evaluates its own outputs using a set of rubrics. This allows the model to align with nuanced human preferences, such as helpfulness, creativity, and factuality.
The self-critique rubric reward is a novel idea. How does it work in practice?
In practice, the model generates responses for various prompts, and the critic model ranks the results using pairwise evaluations against a combination of core, prescriptive, and human-annotated rubrics. The critic is continuously refined using verifiable signals from RL training, grounding subjective judgments in objective data. This closed-loop process ensures robust and scalable alignment with complex human objectives.
That's a holistic approach to model alignment. What about the RL algorithm itself? Are there any unique features?
The RL algorithm is based on policy optimization, with several enhancements. Budget control enforces a maximum token budget per sample, encouraging concise solutions. An auxiliary PTX loss prevents forgetting of high-quality data during RL training. Temperature decay promotes exploration in early training and exploitation in later stages, ensuring stable and high-quality outputs.
The infrastructure for RL training must be quite sophisticated. How did they handle engine switching and system startup?
They used a hybrid collocated architecture, where training and inference engines share resources on the same workers. A distributed checkpoint engine manages parameter states, enabling efficient parameter updates and system startup. The design minimizes synchronization overhead and maximizes network bandwidth utilization, allowing for rapid engine switching and robust failure recovery.
That's essential for large-scale training. Now, let's discuss the evaluation results. How does Kimi K2 perform on various benchmarks?
Kimi K2 achieves state-of-the-art performance among open-source models on a wide range of benchmarks. For coding tasks, it leads on LiveCode Bench v6, OJ Bench, and Multi-PLE. On software engineering tasks like SWE Bench Verified and SWE Lancer, it significantly outperforms open-source counterparts and narrows the gap with proprietary models like Claude 4 Opus. In tool use tasks, it sets new standards on T2 Bench and ACE Bench.
What about general capabilities and reasoning tasks?
Kimi K2 excels in general knowledge, math, instruction following, and long context tasks. It surpasses open-source peers on simple QA, MMLU, and MMLU Redux, and leads on instruction benchmarks like IAF and multi-challenge. In math and STEM, it achieves top-tier scores on AIME 2024 and GPQA Diamond. For long context factuality and retrieval, it outperforms all open-source and proprietary models on DROP and MRCR.
That's remarkable. How does Kimi K2 perform in open-ended evaluations and real-world user preference?
On the Elm Swiss Arena leaderboard, Kimi K2 ranks as the top open-source model and fifth overall, based on over 3,000 user votes. In open-ended tasks, it achieves state-of-the-art win rates on both hard prompts and creative writing, outperforming all open-source models and rivaling top proprietary systems.
Safety is always a concern with large language models. How did Kimi K2 fare in safety evaluations?
The team conducted extensive red teaming evaluations, covering harmful content, privacy, security, and various attack strategies. Kimi K2 demonstrated strong robustness, especially under complex attack scenarios like iterative jailbreak. While some complex cases had higher passing rates compared to other models, the overall safety profile is competitive, with ongoing efforts to address remaining challenges.
Every model has its limitations. What are the known limitations of Kimi K2?
The paper notes that Kimi K2 may generate excessive tokens on hard reasoning tasks or when tool definitions are unclear, leading to truncated outputs or incomplete tool calls. Performance may decline if tool use is unnecessarily enabled, and the success rate of one-shot prompting in software projects is lower than when using an agentic coding framework. The team is actively working to address these issues.
It's good to see transparency about limitations. To wrap up, what are the key takeaways from the Kimi K2 technical report?
Kimi K2 represents a major advancement in open-source large language models, particularly in agentic intelligence. Its innovative pre-training and post-training techniques, robust architecture, and comprehensive evaluation set a new standard for open-weight LLMs. The open sourcing of both base and post-trained checkpoints will facilitate further research and applications in agentic intelligence.
That's a great summary. Kimi K2 is indeed a milestone in the evolution of large language models, combining technical innovation with practical impact. Thank you for guiding us through this comprehensive review.
Thank you, and thank you to our listeners for joining us on this deep dive into Kimi K2. Stay tuned for more paper reviews and discussions on the latest in AI research.
Until next time, take care and keep exploring the frontiers of artificial intelligence.
To summarize, Kimi K2 is a 1T-parameter open-weight mixture of experts model built for agentic intelligence, leveraging the muon clip optimizer and a 15.5T token high-quality dataset for stable pre-training and combining large-scale synthetic tool use data with a unified RL framework to achieve state-of-the-art performance on agentic and reasoning benchmarks, establishing itself as the most capable open-weight LLM to date.